This is the third episode of Poke A Mon, where real science meets the Pokemon universe. I'm Kyukawobudo, but you can call me Professor Baobab. My expertise is in science communication. You can sign up to my weekly newsletter below to get access to a free step-by-step guide on how to master any subject so you can explain it with ease. Disclaimer: this podcast is in no way affiliated with the Pokemon Company, Game Freak, or Nintendo. I am using Pokemon as a pedagogical tool as it pertains to tangential learning. In other words, I tell stories using Pokemon to capture the attention of those interested in Pokemon while remaining integral to the presentation of scientific knowledge. Today, we'll be talking about particle physics. We'll learn all the particles we know about, namely leptons and fermions. We will talk about forces and force carriers known as gauge bosons. We will break down the physics equivalent of the periodic table, known as the Standard Model. And we will then consider exotic particles which could exist, as well as Galar particles which the Pokemon Eternatus can generate. You probably know everything is made of atoms. However, the difference between the atoms in water and the atoms in salt is due to the number of subatomic particles called electrons, protons, and neutrons. However, even protons and neutrons are made of smaller particles called quarks. Meanwhile, there are forces holding quarks together. Those forces allow protons to be different to neutrons and allow neutron stars to exist. This force, called the strong force, is one of a small number of fundamental forces. What are the fundamental forces and particles? According to particle physics, everything we observe in the universe is made of 4 forces of nature and 12 particles of matter. These particles interact through a handful of fundamental forces, each playing a critical role in how matter behaves and how energy is exchanged. Now, these forces may seem abstract, but they literally govern every interaction, from the way atoms hold together, i.e. the strong force, to the vast cosmic movements of galaxies. This is where the Standard Model comes in. As I said earlier, the Standard Model is like the periodic table of physics. It describes 2 main types of particles: fermions, or fermions, which make up matter, and bosons, specifically gauge bosons, which mediate forces. Fermions include quarks and leptons, while gauge bosons are responsible for the forces that act on these particles and are also known as force carriers or exchange particles, because they cause the exchange of virtual particles. These forces include the electromagnetic force, the strong and weak nuclear forces, and the Higgs field, which is not a force but gives particles their mass. Remarkably, the Standard Model doesn't just stop at describing these particles. It also explains how they interact with one another through so-called quantum fields. What is a quantum field? The word quantum refers to things that are so small, hardly anything imaginable could be smaller. Now, imagine the universe as populated with invisible fields that pervade or stretch across all of space. There's a field for each type of particle. Quantum field theory states that these particles aren't just isolated objects. They are actually quantum excitations of their respective fields. In other words, a particle like an electron isn't a standalone entity. It's more like a ripple or wave in the electron field that fills all of space. This might seem like the wave-particle duality of particles and of waves. For example, a photon used to be described as waves, but until recently has been known to behave like photons. And in the same way, electrons, which are normally particles classically, can be described by waves, as waves, namely by the de Broglie wavelength, which we won't talk about in this episode. Technically, the electron wave function also manifests in the photon field, and by wave function I specifically mean the probability of finding an electron, which is actually related to the wave function squared, the amplitude of the wave function squared. So technically the electron also manifests in the photon field and the other fields, but quantum electrodynamics could have an episode all to itself, so I will end the topic there, just to mention it briefly again a bit later. For all intents and purposes, this approach allows us to explain how particles like quarks and leptons interact with gauge bosons such as gluons and photons. For example, a photon is a quantum excitation of the photon field, more generally the electromagnetic field, which means that electromagnetic forces, like those between electrically charged particles, are the result of these field excitations. The beauty of this framework is that it treats particles and forces as fundamentally interconnected. If the particles did not interact with each other by these forces, then there would actually be completely distinct, unconnected fields. This interconnection provides a nearly unified way of describing nearly everything in the universe. So the standard model has perhaps erroneously or colloquially been referred to as the closest thing to a theory of everything. And indeed, quantum electrodynamics might be one of the most precise scientific theories that has been discovered. Perhaps only with supersymmetry, which we'll talk about just in a moment, could we have a grand theory of everything, where even a quantum theory of gravity exists. And of course I say even because a quantum theory of gravity has eluded scientists for so long, and if only we could have a quantum theory of gravity, then this will solve a wide array of problems that would really accelerate the field of particle physics. In the first trillionth of a second after the Big Bang, the electromagnetic force, which by the way is simply the unification of the electric and magnetic forces, and the weak nuclear force were united by what's called electroweak theory. That was when the temperature of the universe was a staggering 10 to the power of 15 Kelvin, Of course, nothing in the universe is anywhere as hot, perhaps except for in particle accelerators where particles come together at near speed of light, and for just a brief moment, a fleeting moment, almost equivalent to a trillionth of a second, 10 to the power of 15 Kelvin can be achieved, but we have barely achieved something like that as of yet. Nevertheless, as the universe cooled down, something called spontaneous symmetry breaking occurred. So as I said, there was supersymmetry, or there was supposed to be supersymmetry at the early beginnings of the universe. And supersymmetry essentially allows for all of the four forces to be united. Now, when the universe cooled down, that supersymmetry became broken spontaneously. And spontaneous just means like essentially at random, like radioactive decay. You can't necessarily predict what will happen, but you can quantify certain properties that will allow you to essentially predict long-term features of radioactivity, for example. So for example, the half-life, you can say within this amount of time you expect to see half of the number of particles, but you can't say for sure what will happen in the next hour or the next year or the next trillionth of a second. At any rate, it's spontaneous symmetry breaking that caused the unified electroweak force to split into the electromagnetic and weak forces. And naturally, you could expect that gravity would also find itself in this early universe united with these forces as well. But because we haven't got a unified understanding of gravity, i.e. a quantum theory, of course we have a classical theory, but we also need a quantum theory for that unified understanding. And since we don't have that, we can only surmise. This symmetry breaking is responsible for creating massive bosons. By massive, I don't mean that they are massive to the extent that we can perhaps hold them in our hands, but rather that they have mass. So they're not massless like a photon or a gluon. These massive bosons, and I should also point out gauge bosons as kind of a teaser to what I will soon point out, but these massive bosons are namely referred to as W and Z bosons, and they mediate the weak nuclear force. These gauge bosons are, of course, heavier than photons, which have no mass, and their masses are a result of their interaction with the Higgs field. So we know that W and Z bosons interact with the Higgs field, whereas photons do not. It gets more interesting than this. The W and Z bosons were created because of a process known as self-interaction in the quantum fields. Essentially, the fields that govern the weak force interacted with themselves. So the W and Z fields interact with themselves, generating massive bosons, the W and Z bosons. And this is kind of difficult to comprehend in light of the fact that the other bosons, the other gauge bosons, are massless. And it should seem that in order not to break symmetry, that the W and Z bosons should also be massless. But because of self-interaction, essentially you have massive gauge bosons, which is essentially mind-blowing. It's something that really shouldn't exist, but by nature of course, the equations and the fact that these are empirically observed as well to have mass, that these are different from photons, from gluons as well. So this is essentially how symmetry is broken. The W gauge bosons are the carriers of the weak nuclear force, which is responsible for processes like radioactive decay. And we're not going to talk about the difference between the W and the Z bosons, also essentially the different flavors of W bosons as well, because W bosons are actually charged. Well, W and also Z bosons are charged. Z has a neutral charge. W bosons have a positive or negative charge. And let me take this opportunity to just pause and say that I've used the terms boson and gauge boson a lot now, but you might be wondering if they are interchangeable. And I did mention that I teased this a bit earlier. The answer is no. A boson, as I will cover later, is any particle with an integral spin, i.e. the intrinsic angular momentum is a whole number. So +1, +2, -1, arbitrary units essentially. A gauge boson is a boson that is also a force carrier. So there are only 6 gauge bosons that we know of. The photon, the gluon, the W, of which there are 2 types, boson, and the Z boson, and also finally the Higgs boson, which was rather recently discovered, recently as in 12 years ago, but at least it's the most recent discovery. I remember when it was actually discovered when I was just entering high school. So if we return to supersymmetry just for a little longer, we realize that if there were supersymmetric particles at the start of the universe, that they would have observed a singular unified force of nature. That is to say that a singular unified force of nature was not confined to the early stages of the universe, but if we found supersymmetric particles now, today, that they would obey a singular unified force of nature. So there would be a electromagnetic field superimposed with a weak, strong, and the Higgs field, although the Higgs field and the other fields are different in a specific way, which I'll mention briefly in a moment. But it's interesting that we observe all of these forces of nature today in various ways. For example, we observe magnets attracting each other, repelling each other, but we don't observe them electrically repelling each other or electrically attracting each other. But if we had an AC current, we could observe a change in the voltage as time progresses, And that would obviously be different, although if you are cognizant of relativity, you might, special theory of relativity, that you might realize that they're actually one and the same. Although let's not go into that right now. At any rate, if supersymmetry did exist, if we were able to discover it, of course this would naturally solve many problems that are like multi-million dollar problems in the context of particle physics, at least, such as what is dark matter, and as I've mentioned several times already, how does gravity fit in? What is the quantum nature of gravity? Why is it so weak? Eternatus is by far the largest Pokemon in the Pokemon universe, and when in its Eternamax form, it is said to release infinite amounts of energy and warp space-time. This is awfully reminiscent of a black hole, but I talked about black holes in the previous episode. Here I want to mention a kind of particle that may or may not be supersymmetric, known as a Galar particle. Galar particles are a kind of gauge boson that seem to interact with the photon field as they glow red, the W field as they cause Pokemon to undergo an unstable transformation similar to nuclear fission, albeit in reverse, the strong force as they cause Eternatus's core to have physical properties that suggest it is made of a unique substance, i.e. protons were added to it, so it doesn't behave like, it behaves like a unique element essentially. And the Higgs field, as they cause Pokemon to have increased mass. Due to this technicality of quantum field theory, Galar particles do not necessarily have mass by themselves, while there is no special interaction with Pokemon or a particular kind of food. And notice that, as I said earlier, as pertaining to quantum field theory, that every particle has a field. So as long as Galar particles are not interacting with the particle fields, the particular field of these particular Pokemon or foods, that they're not going to actually have the same properties. And in that way, it might be that they actually break symmetry, but of course this is not. There's no way of knowing this for sure without actually doing an experiment to show that, for example, Galar particles are left-handed or right-handed, that they have chirality, which I won't actually go into for the scope of this episode, but it basically dictates whether it will break symmetry or not. So now that we've covered the basics of forces and particles, let's talk about how we actually visualize these interactions in particle physics. One of the most useful tools physicists have for understanding particle interactions is something called Feynman diagrams, although there are others. These diagrams, named after physicist Richard Feynman, are a way to represent the behavior of subatomic particles graphically. Think of Feynman diagrams as blueprints for particle interactions. Each line in the diagram represents a particle moving through space and time, while the points where lines meet are interaction points known as vertices. Here, particles can exchange force carriers like photons or gluons, technically virtual forces virtual force carriers, but again, that's a technicality that I'll just leave as is. The diagram helps physicists calculate the probabilities of these interactions. And in short, Feynman diagrams provide an intuitive way to simplify and visualize the otherwise complex mathematics of quantum field theory. In other words, Feynman diagrams actually show each aspect of a complicated equation in the form of a line or a vertex or a squiggly line. These equations are from quantum electrodynamics. That's ultimate precise theory that I mentioned earlier. One of the most common processes you will see in a Feynman diagram, if you're a physics student, for example, at a university or even at A level, is particle decay. In particle physics, decay refers to the process by which unstable particles transform into other lighter particles. And for example, you probably will know that uranium can undergo particle decay, and when it does so, it turns into lighter particles such as krypton and thorium. For example, a muon, which is a heavier cousin of the electron, and we'll talk about the relationship between a muon and an electron before long. The muon decays into an electron, a neutrino, and an antineutrino. Antineutrino obviously being the antiparticle equivalent of a neutrino. This decay happens because the muon is unstable. Actually, the electron is obviously very stable. In fact, it's basically not unstable, like it doesn't decay. But any electron like cousin, like the muon, is going to be unstable, actually highly unstable. It will very quickly decay into an electron. So the reason for that is simply because being heavier, quite much heavier actually, 200 times heavier, it can't maintain its energy state forever. Even for a brief period of time, and eventually releases its energy in the form of lighter particles, which can maintain their energy forever, or at least for a very long time, to the extent that we haven't seen an electron or a neutrino decay before. Speaking of decay, most decays occur through the weak interaction. One of the four fundamental forces we mentioned earlier, the weak force is responsible for processes like beta decay. In general, radioactive decay, and beta decay is one of them, where a neutron decays into a proton, electron, and a neutrino. Yes, a neutron can decay into a proton, but that doesn't mean that a neutron is unstable. This is crucial for processes like radioactive decay, which plays a major role in the stability of atomic nuclei. As I already alluded to, the nuclear fission of elements like uranium, specifically a specific isotope of uranium. Unlike the strong or electromagnetic forces which operate over much longer distances, the weak force only operates at very short ranges on the scale of subatomic particles, because the weak force is mediated by massive gauge bosons. So notice that difference. The strong and electromagnetic forces operate over long distances. Actually, the strong force operates over a short distance also, But because the W and Z bosons are massive, they are limited to a small range. Even though it's called the weak force, its effects are still incredibly important for particle interactions and nuclear processes. As a side note, gravity is much, much weaker. For comparison, the weak force is like carrying the weight of the world on your shoulders, while gravity is like lifting a feather. Nobody understands why, as we don't yet understand gravity at such a precise level yet, as I've already mentioned. Let's talk about the strong interaction next. Also known as the strong nuclear force, this is the force that holds the nuclei of atoms together. If you've ever wondered how protons, which are all positively charged and should repel each other by the electromagnetic interactions, manage to stay tightly packed in an atomic nucleus? Well, the answer lies in the strong force. And the strong force truly is strong, hence why nuclear fusion releases so much energy. The strong interaction is mediated by particles called gluons, which bind quarks together inside protons and neutrons. What's fascinating about the strong force is that it gets stronger as quarks try to move apart. Unlike gravity or electromagnetism, where forces weaken with distance. This behavior is known as confinement, meaning quarks are always tightly bound together in groups of 3 to form protons and neutrons, although we will see quarks can be bound in groups of 2 as well, but those are much less stable. Without a strong force, matter would not exist as we know it. There wouldn't be atoms, there wouldn't be molecules, and of course there wouldn't be life. So we've covered the fundamental forces and how particles interact. But what about the particles themselves? These are known as fermions, and they are the building blocks of all matter in the universe. And on a side note, I'm obviously talking about light matter as opposed to dark matter, since we obviously don't know much about dark matter. So light matter is the matter that we can see, that we know. Interestingly, dark matter is purported to actually compose the vast majority of the universe. But again, we don't know much about it, so that's all that I can say about it for now. Unlike the bosons that we've talked about, which mediate forces, the gauge bosons specifically, fermions are the particles that form the stuff we interact with every day. And ultimately, they give rise to atoms. One key characteristic of fermions, but also of bosons, is their spin. In quantum mechanics, spin refers to a type of intrinsic angular momentum, not an actual spinning motion like a spinning top. Fermions always have a spin of plus a half, which distinguishes them from a bosons, which actually can just have any whole number of spins, like 1 or 0, even -1, or any integer number. This property of spin plays a crucial role in how fermions behave, particularly when it comes to occupying space and energy levels. So we're going to talk about a highly important principle that essentially allows matter to form and allows us to be distinct from the ground and every other object. and this is known as the Pauli exclusion principle. This principle was defined by Wolfgang Pauli, a physicist, and it states that no two fermions can occupy the same quantum state at the same time. So if you have two electrons in an atom, they can't have the exact same set of quantum numbers. And we'll talk about quantum numbers shortly. So they can't exist in the same place at the same time, basically. This principle is why electrons fill different energy levels, also known as orbitals, around an atomic nucleus. So you can see here how physics determines chemistry. Without the Pauli exclusion principle, essentially there will be no difference between fermions and bosons, because bosons have the property of being able to collapse in on itself, and essentially multiple bosons can have the same quantum state. So you can cram into a single point an infinite number of photons or an infinite number of gluons. An infinite number of photons is essentially how a laser is built. And that couldn't happen if bosons obeyed the Pauli exclusion principle, because the photons would be separate because they couldn't occupy the same quantum state. But things like electrons can't behave like light unless they are under specific conditions. And this is interesting, actually. Under certain conditions, particles, fermions, can behave like bosons and obey properties that are considered unique to bosons, so-called boson statistics, and essentially violate the Pauli exclusion principle, although they're not really violating the Pauli exclusion principle, because the Pauli exclusion principle is defined for fermions. When an electron starts to behave like a boson, it actually becomes a boson. For example, when superconductivity is achieved, the electrons behave like bosons and collapse in so-called Cooper pairs. And many electrons suddenly behave like just one moving electron, like one electron. And it's clear that Galar particles are bosons because when all the Galar particles in the region entered Eternatus' core, the core didn't change in size, which suggests that those bosons, those Galar particles, actually were all condensing like a Bose-Einstein condensate. Something that I'll mention briefly at the end. But basically, again, fermions can behave like bosons. But in this case, I'm saying that Galar particles are likely already bosons because of what I mentioned earlier about them interacting with all of the different bosonic fields, the photon field, the W field, the Higgs field. But if you look at the standard model, you will see that under the section called leptons, okay, and we'll talk about leptons as well. A lepton is actually just a kind of fermion. But the electron is the most well known of the leptons. The others are basically just the quarks. So there are three kinds of electrons, essentially. Three cousins, if you will. The electron, of course. But then there's also a heavier muon. And there's also a heavier tau. Okay, so there are three generations. The electron coupled with the electron neutrino, the second generation, the muon, which is about 200 times more massive than the electron, coupled with the muon neutrino, and the tau, which is about 3,500 times larger than the electron, or I should say more massive than the electron, and again coupled with the tau neutrino. It's not just that. In the first generation, we also have the quarks. So the first generation of quarks are the up and down quarks. Perhaps that's if you knew anything about quarks, that's probably the first two quarks that come into your mind. And these quarks make up protons and neutrons. So notice that alongside the electron, the up and down quarks are the most. This first generation of particles are the most stable, and in fact, really the only ones that are stable, because that's essentially all of matter. All of matter is essentially made of up and down quarks, protons and neutrons. So a proton is two up quarks and a down quark. A neutron is two down quarks and an up quark. Or alternatively, a proton is UUD, up, down, and a neutron is DDU, down, up, or UDD. You could also have antiparticles of the same nature. So antiprotons would be anti-up, anti-down, etc. And again, these are all the lightest fermions. So as we go heavier than this, we move up the generations and we become less and less stable, quite dramatically so. So for example, the second generation of quarks are called the strange and charm quarks, and the third generation is called the top and bottom. And there's nothing else I can say about these because we don't know of any matter that is made of strange and charm quarks, really, or top and bottom quarks. And certainly no terrestrial matter, no matter that like you can just go and touch. Of course, the way that we know that these exist, because as I've alluded, they don't exist in nature anymore, or maybe they do in very fleeting amounts. We can produce them in particle accelerators, but sometimes they do occur in cosmic events, for example in supernovas, maybe even in cosmic rays, like in sunbursts from the sun, for example. So there are ways to detect these particles, but they just decay so quickly. They decay for all intents and purposes immediately as they're produced. But obviously you can imagine that scientists have come up with ways to detect things on the order of nanoseconds, femtoseconds. So we are able to detect such things. For example, like how can we know what happens in the first trillionth of the universe without having an instrument that is able to detect such timescales or the mathematics to be able to do that. Now let's talk about how these particles and their interactions are governed by certain rules known as the conservation of quantum property. Just like how energy is conserved in classical physics, certain quantum properties must be conserved in particle interactions. For example, spin must always be conserved. If a particle decays, the total spin of the resulting particles has to add to the same as the original particle's spin. Some other conserved quantities are obviously energy, but also linear momentum. So not just angular momentum, which is spin, but linear momentum, lepton number, and this lepton number is actually more nuanced. So we have the electron lepton number, the muon lepton number, but for all intents and purposes, it's just the lepton number. A similar thing with some others as well, but this is not an exhaustive list actually. A baryon number, charge, electric charge, and color charge, which is also just known as color, but specifically it's not visual color. It has nothing at all to do with visual color, but it's rather color charge, which is a quantum property carried by quarks, and this must be conserved in interactions mediated by gluons. So only particles that interact via the strong force can even conserve this property. It makes no sense in other situations. So these conservation laws are obviously critical for understanding how particles behave and interact. Whether a particle decays or two particles collide, these quantum properties determine what outcomes are allowed and which are forbidden. So we can actually determine the kind of results that we would get from colliding two particles just by understanding the conserved quantum properties. Okay, let's talk about quarks. Quarks are unique in that they don't exist freely in nature. You will never find one quark. Perhaps in a similar way as you might never find a magnetic monopole, but magnetic monopoles are one of the issues that we're yet to resolve in particle physics. So they could exist, but for now, we know that you cannot observe a single quark, at least in nature. They're always confined within larger particles, and they're either confined in pairs, known as mesons, or in triplets, known as hadrons, and known as baryons, actually. Hadrons are mesons and baryons collectively, and mesons are pairs of quarks, baryons are triplets. Baryons are generally more stable, but mesons have been observed to exist. For example, the kaon, which we will talk about later, which actually caused a Nobel Prize to be won because it resulted in the discovery of a particle that broke CP symmetry, and we'll talk about all of this before long. But I've already mentioned symmetry breaking, and CP symmetry is just a kind of double symmetry, if you will. But again, I will talk about that a bit more later. The most common type of hadron is, of course, the baryon, because it's what protons and neutrons are made of. But a meson is actually made of a quark-antiquark pair, so it's always made of antimatter. That matter-antimatter pair. A meson cannot be made of just two quarks, for example, because it will break one of these quantum properties that I mentioned earlier. Tangentially, mesons are actually a kind of boson, simply because each quark has a spin of a half. Antiquarks also have a spin of a half, but so obviously together they have a spin of +1, but they're not gauge bosons. They don't mediate forces. In particle physics, quarks carry a property called color charge. This is simply, again, because of the strong force. There are 3 variants of color charge. Don't be confused or be deceived, but they are called red, green, and blue. So for a hadron to exist, the quarks within it must combine in such a way that their colors cancel out to form a neutral color charge. So physicists, maybe like colloquially, they'll refer to it combining to form white, but just be very careful and observant that actually these are more like vectors. I think it's better to think of a red vector being like a 120-degree angle from the horizontal, a green vector being 240 degrees, and a blue vector being at 0 degrees, 360 degrees. And so if you combine them, then they would cancel out. You will get a vector with a magnitude of 0. It's the same with mesons as well. So if you have a vector that is pointing in a certain direction and the other vector is pointing in the opposite direction, so let's say you have another vector that is pointing 60 degrees to the horizontal, and then you have another vector that is pointing 60 plus 180, so 240 degrees, such that it's pointing directly like in the opposite direction, then they would also cancel. Next, let's talk about leptons. And we have already deduced that leptons do not interact via the strong force. They completely ignore color charge, so they don't have that same interaction that the quarks have, although they do share some things. For example, their interaction with the Higgs field. There are 6 types of leptons that I've already stated: the electron, the muon, the tau, and their corresponding neutrinos. Each lepton has their own unique quantum number, and obviously these have to be conserved. So, for example, if an electron and a neutrino is produced from a kind of decay, that neutrino has to be an electron neutrino, because an electron neutrino has an electron lepton quantum number of -1, where the electron obviously has a +1 lepton quantum number. Leptons are fascinating, perhaps because of their simplicity. So the electron obviously being essentially the mediator of chemical reactions, of all the things that make molecules work, and so forth. is powered by, and it powers also electricity by interacting with the photon field as well as and the electron field. So essentially the electromagnetic field. Neutrinos barely interact with matter at all. In fact, there are as many as 40 billion neutrinos that are passing through us, through your body, every second, and you are not. Another interesting feature about neutrinos is that they're more numerous than photons. Yet, despite this, they are so elusive that they pass right through the Earth and our bodies without ever interacting. Or perhaps they interact, but very, very rarely. Neutrinos do carry mass, but they don't seem to interact with the Higgs field, which is interesting. It was actually a recent discovery that showed that they do have mass, and the mass, there is an upper bound to the mass actually, but nevertheless, the fact that they don't interact with the Higgs field means that they have mass via a completely different mechanism that we haven't discovered yet. It's almost as if they have their own secret way of being a part of the universe, interacting only weakly with the rest of it. Galar particles also barely interact with matter, as they only interact under certain conditions, like at power spots, where there is a high local concentration of particles, or perhaps when Eternatus causes the darkest day, and the concentration of particles everywhere increases. Perhaps if they didn't interact with the Higgs field also, they would be just like neutrinos, in that they wouldn't be able to linger or interact with anything at all. Since what would be the purpose of Dynamaxing and Gigantamaxing if you can't even grow in size? Now, we can't talk about particle physics without mentioning the gauge bosons. Fully exploring it, I should say. The particles that mediate the fundamental forces typically have a spin value of +1. They don't follow the Pauli exclusion principle as I mentioned, but rather boson statistics, where multiple bosons can occupy the same quantum state, and that produces their own fascinating, their own host of fascinating properties. Perhaps the best known of these gauge bosons is the photon, but of course we've already seen the W plus, W minus, Z naught bosons, the charged W bosons are the neutral Z boson, which are massive gauge bosons, and the Higgs boson, which doesn't actually mediate a force, but rather the Higgs field is a scalar field. So the Higgs boson actually has a spin of 0. It's the only gauge boson with a spin of 0. It was discovered in 2012. And unlike the other forces, or rather the other fields, the Higgs field is a scalar field. The others are vector fields. Hence, a force is a vector. Mass is a scalar. It doesn't have a direction. The gluon is actually more interesting there's actually some more interesting features of the gluon. Specifically, there are 8 types of gluons. So they have a color anti-color charge, which just means that they interact with other gluons as well as with quarks. But that's really a technicality. Really, it's just the gluons interact with quarks. They mediate the strong force, allowing quarks to bind together. Also, interestingly, while we've discovered the particles that carry these three fundamental forces, there's again no confirmed quantum description of gravity. The hypothetical particle would be the graviton, and you might have heard of that before, but we haven't yet observed it up to now. We've observed gravitational waves when two black holes collide, when they move quickly, a really massive body like a black hole moves quickly, it releases gravitational waves, and that's what happens when black holes are spiraling into each other and finally collide. But a graviton is actually not a gravitational wave. It's quite different, and we haven't discovered it. So we don't have a quantum understanding of gravity. We don't have a solid understanding that allows us to integrate that such a quantum description of gravity into the existing standard model. Finally, it's worth noting that bosons follow a different set of statistical rules than fermions. This is because of their total spin being an integer rather than a half integer. And these statistical rules, of course, are known as boson statistics. So the helium-4 atom, even though it's an atom made up of protons, neutrons, quarks, up quarks, down quarks, even electrons, that behaves as a boson because altogether the total spin adds up to an integer. Bosons are governed by Bose-Einstein statistics, such bosons. So obviously quantum gauge bosons are just gauge bosons. They already abide by boson statistics, but bosons that are typically cooled to very close to absolute zero will become a Bose-Einstein condensate, which is essentially like a fifth state of matter, if you will, after solid, liquid, gas, and plasma. This allows the bosons to be cooled and condense into the same quantum state, apparently violating the Pauli exclusion principle, but again, they become bosons. So we see phenomena such as helium-4 becoming a superfluid close to absolute zero. Notice close to absolute zero. So at room temperature, even though it is a boson, it doesn't actually exhibit these properties of being a superfluid, of being a Bose-Einstein condensate, following Bose-Einstein statistics, boson statistics. And a superfluid is a fluid that, for example, exhibits no friction at all, which allows helium-4, which is a fluid, to creep up the sides of the container that it's in. Okay, the final part is exotic particles, of which Galar particles will be the last thing that we mention, but these particles don't fit into the standard model. They may have existed, or they did exist in fact. they would have existed only briefly right after the Big Bang during the first trillionth of a second. Everything happened in the first trillionth of a second, as you would have come to realize. When, of course, the universe was extremely hot, 10 to the power of 15 Kelvin, and also extremely dense as well, because there was just so many particles in a very small amount of space. And then the Big Bang, if you're familiar, the universe expanded like by many times in just a moment, in the twinkling of an eye, essentially. Most of these particles decayed essentially immediately, and the supersymmetric particles would have been among them, and only the stable particles remained. And the stable particles that remained are basically just that first generation in the standard model: electrons, up quarks, and down quarks. Of course, that doesn't mean that exotic particles are gone for good. We could still see them in high energy cosmic events, so that's hence we have been able to detect muons, tau, and bottom, top, strange and charm quarks, and of course particle accelerators have helped us to discover those. I've come all this way without referring to without talking much about antiparticles, so let me mention them now. These are actual particles that have been shown to exist, unlike dark matter. Dark matter is still an elusive thing in the universe that should exist, but we haven't formally detected yet. But we have formally detected antimatter. And in fact, we've seen antimatter. Like we have detected antiparticles in the Large Hadron Collider, for example. One of the most famous particle accelerators. One of the most intriguing ideas is obviously the existence of antiparticles, not only because it's a whole new realm of particle physics, essentially, with every particle having an antiparticle equivalent counterpart with the same mass, but essentially opposite everything else, every other quantum number. So opposite charge, opposite color charge, opposite lepton number, opposite baryon number, etc. But according to the quantum electrodynamics, antiparticles move backwards in time. Okay, not backwards in time literally, like they're going backwards in time. They're reducing the amount of entropy in the universe, which is essentially going backwards in time. What it means is that they are going back. They can be interpreted as going backwards in time if you solve the equations. In the equations, you can consider the same particle but just going backwards in time, and you will reach the solution for an antiparticle. Most interactions in physics respect a set of symmetries known as charge, conjugation, charge C, and parity, P symmetries. Meaning that, okay, so for charge, flipping a particle's charge, changing the charge, so the conjugate, the opposite, or reflecting it like a mirror image, so again, changing the coordinates, reversing the coordinates, doesn't change the physics of the interaction. So it would still essentially be the same particle. It would be a reversed particle or whatever, but the interaction would be the same. However, there are certain particles actually, namely the kaon, again, which caused the which produced a Nobel Prize, that breaks both symmetries at the same time. This is known as CP symmetry violation, and the CP together means that the only way to get back a particle that has the same properties as a kaon is to reverse the charge and also reflect the mirror image. So you can't simply just reverse the charge, that won't do it, but you can't just reverse the mirror image. This actually is important because it helps explain why the universe has more matter than antimatter. Before this, and hence why it got a Nobel Prize, it wasn't clear why we have more matter than antimatter. Because in the beginning of the universe, the same quantity of matter and antimatter was generated. Kaons help us to understand why, but of course we could always do with more evidence. Amusingly, Galar particles can be contained as well, just like a Bose-Einstein condensate, where particles behave as if they are in a single quantum state. In the Pokemon world, this kind of superposition could explain why certain Pokemon can Dynamax in power sports, where Galar particles are highly concentrated and can be controlled through technology like the Dynamax band. Of course, I've already supposed that Galar particles are gauge bosons, so they're not like particles, but in case they were like particles, then this could also explain how it would work. By controlling the quantum state of these particles, trainers can unleash powerful transformations in battle, like using a laser to produce an intense beam of coherent radiation. Unlike most bosons, extremely low temperatures are required to maintain their collapsed quantum states. However, the search is on, for instance, for a room temperature superconductor. So it is possible that Galar particles could also be physical particles from presumably the meteor Eternatus came from, that readily become a Bose-Einstein condensate at room temperature and just so happen to concentrate in particular regions, perhaps where there are disturbances in space-time. If you've come this far into this episode, please consider liking this on Spotify, Apple Podcasts, etc. This will help me tremendously and cost nothing but a few moments of your time. In this episode, we explored particle physics through the lens of Eternatus and this generation of Galar particles. We covered the standard model, explaining how particles are quantum excitations of fields, and introduced fermions and bosons. We discussed the role of quarks, hadrons, and gauge bosons in mediating forces, including photons and the Higgs boson. You can find the resources I consulted while researching for this episode in the show notes. Isn't the power of science simply amazing?